Okay, so here's what we saw in our weathering a rocks lab. We saw the different rocks break down differently. Now the question is going to be why. Why are some rocks strong and why are some rocks hard? Well, it all comes down to what rocks are made out of. And that leads into our discussion of minerals, because minerals are what make up rocks and what makes one rock different than another rock. So before we can explain rocks, we need to understand what minerals are. On the sheet of scratch paper that you pick up as you came in the classroom, on one side we want to label it vocabulary. Anytime you see a red bold word on the PowerPoint, you need to write that down and record the definition of that term. On the right, we're going to have concepts. These are big main ideas that I expressed throughout the presentation. First of all, a definition of a mineral, and this is very specific. You need to read it and write it very careful. A mineral is a naturally occurring inorganic solid with an orderly crystal structure and definite chemical composition. Blah, blah, blah. That sounds really long and complicated, but we're going to break this down piece by piece and explain why this wording is important. First of all, the characteristics to be a mineral, which fits into the definition. First of all, it must be natural occurring. Nothing man-made is a mineral. Second, it's got to be a solid. Liquids, gases are not considered to be minerals. It must have an orderly crystal structure. So one of the requirements to be a mineral is that it must have an orderly crystal structure, which is just a fancy way of saying that it is put together one particular way. And we'll use some Legos as an example. Notice I've got 3 Lego pieces, and I have arranged them that particular way. That can be representative of a mineral. Now, I have those same 3 Lego pieces, but I have them arranged differently. This would be an example of an entirely different mineral because the blocks, the Lego pieces, are only arranged in this pattern versus this pattern. So a crystal structure is just a fancy way of saying how are the pieces or the atoms that make up that mineral are arranged. And each mineral has its own way in which its atoms are arranged, and that's what makes it that particular mineral. It must also have a definite composition, which just means it has a recipe. Another requirement to be classified as a mineral is that it must have a definite composition. A definite composition is just a fancy way of saying what is its recipe, what are its ingredients, what is put together in a certain way to make that mineral. And you notice all of these are blue and yellow Lego pieces, but they all have a specific recipe. This one is 2 medium blue rectangles and 1 yellow square. This is 2 yellow rectangles and 1 smaller blue rectangle. Each one of these is made up of its own particular set of pieces. It has its own recipe, and that's what must be true in order for something to be classified as a mineral. It must be put together with its own set of ingredients, and that's what makes it that particular mineral. Must also be inorganic, which means it is non-living. So plastics, coal, water, not considered to be minerals. Plastics are man-made and they're not really true solids. Coal is an organic material. It came from living things, and water, of course, is a liquid. Granite, not a mineral. Granite's a type of rock, and it's definitely not a mineral because these are all examples of granite, and you can look at them and you can see they're all very different. It doesn't always have the same composition. How many minerals are there? This is a big idea, concept, about 3,800. Now, these minerals, they're formed naturally. Well, the question becomes now, how did they form? How do we get one mineral versus another? They're only formed pretty much one of 4 ways. We're going to list and describe these. First of all, crystallization. Crystallization is when minerals clump together from the cooling of magma.
So here I am in East Iceland. And if you didn't know, Iceland is entirely one big huge volcano. And all of the rock that makes up Iceland was either magma or then lava that came to the surface and cooled. Now, one of the ways in which minerals can form is from the cooling of magma or lava. And what happens is, as the magma or lava starts to cool, different stuff in that mixture cools faster or slower than others. So you start to get little clumps of material that are all the same. And remember, that's what a mineral is. So behind me, you notice all of this dark rock, and here we've got a sample of lava that cooled into a rock. But if you see right here, we've got this little chunk right here that is all white. This is where a bunch of silica started cooling together and clumped and made this mineral. This is the mineral quartz. And it formed because this silica cooled at a different rate then the rest of the rock and it all clumped together. And you can find it all over these rocks all around me. Eventually, the mineral can break off and you get quartz. This is the mineral quartz, and it was formed from the cooling of magma or lava. That's how it got here. That's the only way in which quartz forms.
So as magma cools, different stuff we know cools at a different rate. Water we know doesn't cool down as quick as, say, a metal. And as things cool down, they harden from the liquid form in the magma and they clump together, and that's how we get big collections of minerals. Here you can see it. You can see this right here. That's a chunk of olivine. That's a green mineral that clumped together as the magma cooled. Over here in this rock, you can see here's some black stuff, we got some pink stuff, and we got some white stuff. Those are all different minerals that cooled and clumped together at their own rate when the magma was cooling. Now precipitation is the second. It's not precipitation like rain.
So let's talk about how some rocks are made. We're going to look at this nice sedimentary rock called limestone, and it was formed via precipitation. And when we talk about precipitation, we're not talking about water that falls out of the sky, comes down here and makes rock. That's not what precipitation means. In this case, precipitation is when you get a rock formed by the minerals that are being carried by water. So this is merely a big clump of minerals that was left over from the water. Well, where did the water go? Well, it's not that easy of a process. It all starts way back up in there. It snows a lot, and under pressure and as the snow melts, the water goes into the ground. We know that. Well, it comes down here to this very low point and the water starts popping back up out of the ground. That's why we have this lake here. This is why we have springs. This is a spring-fed lake. Well, when the water popped up out of the ground, it was carrying minerals. Well, lake water is very, very slow water. So once the water popped up into this lake, it could not carry its minerals anymore. So it just started to drop them. And as the minerals were dropped, they clumped together. And a clumping, hardened chunk of minerals is what a rock is. So this process is called precipitation. It's when water drops the minerals it's carrying and we wind up with a big hardened collection of those minerals, which is what a rock is.
The residue from hard water that we talked about earlier in the semester is a good example of how minerals form by precipitation. The water goes away and it leaves the minerals behind. This can happen underground because water is moving through the ground. Water finds a little hole in rocks. We know there's holes and open spaces in rocks. Well, the water leaves some of the minerals behind, and you get little clumps of minerals within little open spaces in the rocks. Stalactites and stalagmites. When water falls into a cave and the water starts to drip from a rock, like over here, well, some of the minerals get left back here. They get left behind. And these collections of minerals that were dropped by water are minerals. Halite, salt, table salt that we put on our food is formed primarily by precipitation. What happened is we had a big saltwater ocean and the land changed. And in this area here, it's now dry land. There's more water, say, in glaciers, like after the Ice Age. Well, the water evaporates, and what's left behind is the salt. So we have places that used to be under the oceans that now have huge collections of salt sitting there. That's minerals forming by precipitation. In the middle of our country here, we used to have a big ocean at one time, and that was salt water. Well, that ocean obviously went away, but the salt stayed behind. So in this part of the country, we have huge collections of salt because the water evaporated, leaving the minerals behind. That's mineral formation by precipitation. This is actually how we get our table salt. We have huge mines in the middle part of our country, especially in Kansas. We dig down there, and where all that salt had precipitated, we just now dig it out of the ground, and we've got a big chunk of salt. Salt is formed by precipitation. A very common mineral formed by precipitation is exactly what I just said, sodium chloride. It is found under the ground, and if we mix it with water, leave the water evaporate, what's left behind is the salt. You can actually get table salt from salt water. You just set it out in the sun, water goes away, and we're left with the mineral sodium chloride.
So let's talk about another way in which minerals are formed, and that method is going to be called hydrothermal alteration. Well, alteration means to change something, and hydrothermal refers to hot water. Now, if you see behind me, we've got steam coming out of the ground. This is at the top of Kilauea volcano in Hawaii, so there's a lot of heat under the ground. Well, it rains a lot here. The water goes into the ground, comes back up as steam. So there's our hot water. Well, all of the rock in this area starts off like this. This is all we've got, this black basaltic lava rock. Well, that hot water, that hydrothermal part of this equation is coming up out of the ground. And when that hot water comes up out of the ground and comes in contact with this black rock, it chemically alters the material and it makes new minerals. And that's the yellow that you see right there is sulfur. We got some hematite here, which is reddish brown, and then we've got some white, which is gypsum. Now, none of that stuff was here naturally. It was formed from this basaltic rock when it came in contact with that hot water coming out of the ground. So once again, this is an example of minerals being formed by hydrothermal alteration.
So there's our definition of hydrothermal alteration. When we see this a lot around hot springs, we see huge collections of minerals, and that's when the hot water was coming up out of the ground, and it reacted with the stuff in the ground, and it brought the minerals to the surface, and then they clumped together. Another example from a hot spring, big, huge collection of minerals that came up out of the ground. You can see in these pictures here, the yellow that you notice in these pictures is when the water came up out of the ground, the hot water, the steamy hydrothermal solution, well, it cooled and it dropped some of the minerals that it was carrying, and it formed the mineral sulfur.
So you can see collections or streaks of a particular mineral that runs through the ground, runs through this rock. You can see this here. All of these white minerals are in a line that kind of runs through the body of the rock. This happened either one of two ways. Either this was a hot hydrothermal solution that found its way in a crack in the rock, or this particular rock was heated and squeezed and made all the white minerals, all the white atoms come together and form that mineral right there. Either way, what we have now is a streak of one mineral that runs through the whole rock. This streak or line of minerals that goes through the rock is called a vein. Just like the veins that run through your body that move blood, this is a vein of minerals, which is a streak or a line or a collection of materials that runs through a rock.
Here you can see some other examples of veins. We can see it runs through the rocks. We get little places where the water especially can go, and then it drops the minerals, and we end up with a little line there of minerals. It's called a vein. A geode. Geodes are also formed by precipitation, and if you've ever seen these in a rock shop before, they're a hollow rock. They were a rock under the ground where there's some open space and hot water got in there, or water took some minerals in there, and then the water eventually seeped out, evaporated, and we're left with some crystals behind. Those crystals are minerals that formed probably by a hydrothermal solution that then precipitated. Here's a geode in Iceland. You can see them in the rocks. You can see the little hole in the rock where the water was able to get in there and drop its minerals. The final method is changes in pressure and temperature. Because deep underground you've got a lot of heat and pressure constantly bending and folding and breaking the rocks, sometimes that can cause the minerals to form because the stuff underground gets rearranged. And remember, being a mineral is all about how the stuff is arranged.
So here we have a big chunk of rock that at one time was deep underground. And it was just a kind of a molten collection of material together called magma. And it hardened, and it formed a big hardened chunk of rock. Well, something happened to this rock, and that over time it was squeezed and pushed and bent and heated, and the rock was actually changed. This is why this rock has kind of a wavy, curvy appearance to it, because it was squeezed over time. And what happened was all the different materials gathered together differently. You can see this right here is a bunch of material that all looks very similar. Those were all those atoms that got squeezed and heated, and they came together and made this material, which is different than this material. This is a mineral. This mineral was formed because of changing heat and pressure under the ground. Before this rock was squeezed and rearranged, it all looked the same. But because it was heated and squeezed, it formed this mineral by making all of these white atoms come together and arrange themselves in a particular pattern that we now call that particular mineral.
Here are three examples of carbon, but in each case the atoms were put together in a little bit different pattern, which means they're a different mineral. Carbon can be the mineral diamond, it can be the mineral graphite, or it can be just what's called amorphous carbon. And all has to do with how were the minerals squeezed together. Now the characteristics of minerals are described by using a couple specific characteristics. First of all, we describe minerals by their color. So let's talk about color for identifying minerals. We have some real limitations with color because we can have a bunch of different minerals that are all red, like with our Lego pieces here. These are all red. They have the same exact color, but you notice they have different recipes and they're arranged differently. So these are three different minerals. Color by itself is not necessarily the best characteristic that we can use to identify minerals. Now, if I had this, I can tell the difference between this one and this one by their color, but I can't tell the difference between these two. So color is helpful, but we need more than color when we are trying to pick out one mineral from another. So what causes different minerals? Because sometimes the same mineral can actually have a different color, and color is just how light reflects and interacts with that structure. Minerals can have stuff that get mixed in with them when they form. That stuff is called an impurity. An impurity is stuff that gets mixed in with the recipe. It's not really part of the recipe, but it's just was kind of tossed in there, and that can change how the mineral looks. Quartz is a very famous example. You can have many, many, many different colors of quartz because how its atoms are arranged, it allows for extra little stuff to kind of get caught in the middle in there. And since you have different colors because the different stuff that gets caught in there gives quartz a different color. It's all quartz, but those impurities give it different colors. Beryl is the same way. Think about it this way. You got cotton t-shirts, and they're all cotton t-shirts. They're all the same thing. They're all cotton t-shirts, but each one has a different dye that is trapped in the cotton. That's very similar to how a mineral like quartz can have different colors. It's all the same mineral, but it gets the dye, like in our shirts, gets trapped in between the recipe. Now streak. Streak is a little bit different. Streak is the color of a mineral in its powdered form because sometimes minerals look a different color when they're in a powder versus in a solid. And that's one of the ways you can identify one mineral versus another. Here you can see how you test streak. You rub it onto what's called a streak plate. And we're going to be doing this in the lab. And you'll notice these are all kind of blackish gray minerals, yet they have decidedly different colors once you scratch them into their powdered form. So it's a way to tell one mineral from another when color doesn't help you. Luster. Luster is how does it reflect light? What does it look like under the light? It's like shininess. Is it clear? Is it cloudy? And there are some different terms that we use to describe mineral luster that we need to have in our notes because we're going to have these. We're going to have to use these in our lab when we describe the different minerals. First of all, metallic luster is just what it says. Metallic means it looks like metal, and you know that metals are shiny. You know what metals look like when they are put under the light. Glassy or vitreous. You know what glass is. It lets light go all the way through. So a glassy vitreous luster is one that looks clear like glass. It can be colored, just like glass can be colored, but the light still comes through. Adamantine. This is something we won't use in the lab, but adamantine is diamond-like. It is spectacular. It is, sparkly, which this is a luster that's pretty much just used with gemstones. And that's why we use diamonds for jewelry, because we like the shininess of them, because they have an adamantine luster. Waxy. Pretty simple. It looks like wax. Pearly or milky. Looks like pearls or kind of a milky color. Earthy. Earthy is kind of the catch-all. It's basically what we use to describe anything that doesn't fall into one of those other categories. It's earthy, it's dull, it's dirty, it's whatever. It's basically any mineral that can't be described by one of those other specific lusters. Now, crystal form. Crystal form refers to how the atoms in the material are arranged, kind of like I showed you with the Lego patterns. And this is probably the least useful for us in a practical sense because we can't look at it underneath a microscope to see how actual individual atoms are put together. But each mineral does have its own specific way in which it is put together. We can see some of the results of those arrangements of atoms because it does tend to give some minerals a particular shape, whether it's a cube, a diamond, whatever. Cleavage. Now, mineral cleavage, this is a term specific to minerals. This is the tendency of a mineral to break along flat surfaces. When you hit a mineral with a hammer, it's going to break. And sometimes the atoms break into flat sheets. It has a flat side. That's cleavage. These are examples of mineral cleavage. When you hit a mineral with a hammer and you break it into pieces, it will naturally break into shapes that have flat sides. That is mineral cleavage. You can have a mineral that has cleavage in one direction, two directions, or three directions. Basically, does it have one flat side, two flat sides, or three flat sides like a cube? And we're going to test some different minerals and see examples of ones that have one, two, or three flat sides. Now, some minerals don't have flat sides. They're just jagged. That's called mineral fracture. Fracture is just when a mineral breaks into a jagged shape, or it doesn't have flat sides when it is broken. And that can help you determine what one mineral is versus another, because we know that, hey, mineral A breaks into flat sides, mineral B does not. Conchoidal fracture. Now, there's a very special type of fracture, and that's called conchoidal. That's basically when you get these kind of rounded shapes when things fracture. You can see it, they kind of look like rounded grooves. Hardness. Hardness is basically what it is. It's how hard is the mineral. Technically, it's the resistance to scratching, because that's how we test how hard it is. And what we do is we test it versus a known substance. For that, we use the Mohs hardness scale. And this is just a system. It's just a rating scale to compare one mineral to another. And there's not a hard and fast number to this, but we rate minerals on a scale of 1 to 10. It'd be like rating people by their height without actually measuring them. And we'd have, say, on the height scale, me personally, I would be at the bottom of the scale, and you would say, okay, Weigand's a 1, and we take an NBA basketball player, and that would be a 10, and we can use people in between to denote a relative hardness. Okay, are you taller than Weigand, but shorter than a NBA basketball player? That's how the Mohs hardness scale works. Here are the common items that we use. We have some minerals that we have set on this scale. Diamond is one of the hardest minerals known to man. It's also one of the hardest ones that is easily available. So you can get diamonds even though they're expensive. A diamond is a 10. It's super, super hard. That's why we use diamonds to make drill bits and cut glass. Talc. Talc is so soft down in the bottom that it breaks into a powder basically naturally. We also have some other things. Your fingernail has a hardness of about 2.5, and everybody's fingernails are about the same. A wire nail that we use to build houses with has a hardness of about 4.5. That's steel. Glass has a hardness of about 5.5. So we can compare minerals to these common things that we can get our hands on and say, okay, this mineral is harder than my fingernail, but it's not as hard as glass. And we give it a score, and that helps us identify what mineral we're talking about. Now, the density is how tightly together the minerals put together. How tightly together are the atoms squeezed? And for the most part, in what we're doing in the lab, density is not going to be very relevant to us because we can't measure it very accurately. And the values for densities for most minerals are all very, very similar. But in a chemical laboratory where you're trying to identify minerals, density can be very helpful if you can measure it accurately. We can't in the classroom. Now, the common mineral groups. I don't expect you to copy down this whole chart. What I do want you to have, I want you to have a list of the common minerals, and we will go back later on and fill in what we need to. I want you to have this list of what the common mineral groups are. You don't necessarily have to draw this chart, but I do want you to know this, that the common mineral groups are pretty much determined by what element is the primary element in the mineral. All minerals in there have silicon. All minerals in that group have carbon. All minerals in that group have sulfur. You kind of get the idea here. We have common mineral groups. Minerals are grouped basically based on what are they made out of. What are their ingredients? Because they'll have some common ingredients, and that's how we set up these mineral groups. So at this time, you can bring your notes. I'll give you a copy of the notes check, and we'll take your assessment before we start our mineral identification lab tomorrow.